This is the last video this week, and we're going to take a quick look at set laws. We're going to split this up between this week and next. This week we're just going to focus on the names of the laws and how these go step by step, and next week you're going to take a look at taking a complex set expression and then simplifying it down to something easier to use. So we use set laws to take complex set expressions and to simplify them. If we have 20 sets chained together through intersections, unions, complements, and differences, by hand, it can be very tedious to evaluate the final set. For computers, they don't really care unless it gets monstrously huge. But for humans, even if it's a moderate size or even a small size, it can be very tedious to do by hand. So if I, for instance, want to take a look at, I don't know, say A union the empty set, and then I take the intersection of the universe and the intersection of A together, well, it's probably easier, instead of evaluating all these different things and looking line by line, it's probably easier to just look at the set A, because that's exactly what it evaluates to. So the set laws are just steps we can take to simplify our sets. So I'm not going to go through all of these, but I'm going to explain the intuition behind a few of these and show you how these work with a proof, and just step by step how these go from one line to the next line. So we'll start with commutative and associative. Basically, what these mean is that if you have 2 or 3 sets that are all conjoined by the same operator, if it's an intersection or union, then it doesn't matter what order we do these in. So for instance, let's take a look at commutativity. If I have 2 sets, A and B, no matter if I have A on the left or A on the right, the intersection of these 2 sets are always in the center. So the elements that are shared between A and B are the same no matter if you take A intersection B or B intersection A. Similarly, if we add a third set to it, C, it doesn't really matter which one we do first, because we're just going to end up with this thing in the center. So whether we take A intersection B first, or whether we take B intersection C first and then do A after, it doesn't matter. So I usually like to think of the commutative and associative laws as being like adding numbers. So if I do 1 plus 2, that's the same thing as doing 2 plus 1. If I do 1 plus 2 first and then add 3 to it, this is the same thing as taking 1 and adding it to 2 plus 3, where 2 plus 3 is done first. Both of these things equal 6. In fact, in mathematics, this is called commutativity and associativity. The names are the same whether you're looking at sets, whether you're looking at logic, or whether you're looking at adding or multiplying numbers together. The distributive laws are interesting. So this is when you have 2 different operators, so A or B and C. And I want to think a little bit about multiplying and adding. So let's say I have 3 times 2 plus 4. There's 2 ways I can do this. First, I can do 2 plus 4. I can get 6 together and then multiply that by 3, and that gives me 18. Or I can distribute these. So another way of doing it is I can take 3 times 2 first, and then I can add it to 3 times 4. And if I do this, what I end up with 6 plus 12, and that gives me 18. Okay, so this is called the distributive law, because what we're doing is we're taking this 3 outside and we're distributing it over to the inside. And what's important here is that the operators are different. So this only works in multiplying and adding when you multiply first and then the 2 things added together are done in the brackets. But with set theory, it doesn't matter whether it's intersection inside the brackets or union inside the brackets. So to show this a little bit more clear, if I have 3 sets, A, B, and C, I'm going to write these all out first. So A, B, A, C. I'll show you how this is done. If we have 2 different operators, so let's say union and intersection, so A union B intersection C, I can distribute this. So what I can do first is I can take A union B, and then I can intersect it with the other distributed operator, so A union C. So this is a lot like the multiplication example. So 3 times 2 plus 4. So 3, 2, 3, 4. And I'll use the same colors so you can see this. Let's put these in brackets here. So let me just fill all this out first. So 3 times 2 plus 4 is the same thing as 3 times 2, and then adding 3 times 4. So this can be a union first, or it can be an intersection first. It does not matter in this case. So if we flip out these unions and intersections to make it so that we have intersections here, and we have unions inside, this does not change how we work. So this is a way of expanding sets or simplifying. So these can go in either direction. You can either take a complex expression and simplify it, or take a simple expression and make it more complex. I want to show you what this looks like visually. So here I'm going to build a universe. This is our universe. I'm going to have a set A, I'm going to have a set B, and I'm going to have a set C. And actually what I'm going to do then is I'm going to take this, I'm going to shrink it down a little bit, and I'm going to copy it, and I'll paste this over right here. So on the left side, I'm going to do A union B intersection C, and on the right, I'm going to do A union B, and I'm going to intersect it with A union C. So these are equivalent sets. Now visually, what I'm going to do first is I'm going to take B intersection C. So I want everything that is in both B and C. So this is this area right here. Okay, now I'm going to take the union of it. So I'm going to add in everything in A as well. So I'm going to add in all of this area. So the final set that I'm left with, everything that is in A union B intersection C, is going to be this area here. So I'm just going to outline this in pink. I'm going to make this a little bit darker. So this is the area we're looking at. Now on the right side, here's what I'm going to do. I'm going to do A union B in red. So A union B is going to be all of this area here. So this is everything that is in either A or B. Okay, that covers all of that. Now in pink, I'm going to do everything in A union C. So this is everything that is in either A or C or both. Now what I need to do is I need to take the intersection of these. So I'm going to do that in blue. So basically, the entire area that is covered by both the red marks and the pink marks, that's the intersection. So I want everything covered by both. And if we take a look at this, this is where the overlap is, in this area right here. Now if we take a look at these two pictures, what we have are the same set in the end. So whether it's A union B intersection C, that refers to this entire area. If we have A union B intersection A union C, that also refers to that exact same area. So that's what I mean when I say both of these sets are equivalent with each other. So that's two different ways of representing the same set. So that's the distributive law. Identity and domination laws are just about the unions and intersections with the empty set or the universe. So we did this in the set operation video. If you take like A union the empty set, I want everything that is in either A or the empty set. But of course there's nothing in the empty set, so we're not adding anything to A, so that just gives us A back. If we take A union the universe, that means I want everything that is in both A and the universe. Well, clearly the only shared elements are in A itself, so that also gives us A back. This is called the identity law, because whatever set you put in A with either the universe or the empty set, you just get A back. The domination law is like the opposite. So the empty set or the universe dominate over the particular set you take. So A intersection the empty set, that means I want the elements that are in both A and the empty set at the same time. But this one has no elements. So of course, there can't be anything shared between A and the empty set. So we just get the empty set out. If we do A union the universe, well, here's our universe. Here's A. I want everything that is in either A or the universe. So of course that's going to be the entire thing here. So that gives us the universe. A union the universe gives us the universe back. The complement laws have to do with complements. So for instance, let's say I have A. Well, A complement is everything outside of A. And this whole thing is the universe, right? So if I do A union A complement, well, I'm just looking for everything that is in either A or A complement. And that gives us our universe back, because that's everything in our universe. Similarly, if I want to do A intersection A complement, that means I want things that are shared by both A and A complement. But by definition, everything in A complement is not an A, and everything in A is not an A complement. So we don't get anything. There's no shared elements between A and A complement because they're different things completely. Let's take a look at the next one. So this is A complement complement just gives us A back. So what this says is here's A. Now I want everything outside of A, so that's A complement. Now I'm going to take the complement of that. So I want everything that's not an A complement. Well, that's just going to give us everything back in A. So A complement complement is just the same thing as A itself. So this is like a double negative. Like, if I'm not happy, well, that means I'm happy, right? This is the same thing as being happy. So A complement complement is just the same thing as A. Similarly, if you have, say, A complement complement complement, that's just the same thing as A complement because two negatives cancel out. Okay, finally, what I said before, A minus B is the same thing as A intersection B complement. If you draw a Venn diagram here, well, let's just do the first one. So if we do A minus B is just this area here, right? Okay. So let's instead think about A intersection B complement. So here's A, here's B. Everything outside of B is B complement. So I'm going to highlight B complement just for us to see. So B complement is everything outside B. So this is all of this part. Now I also need to take the intersection with A. So everything that is in A I'm going to do in pink. Okay, so now if we take A intersection B complement, we want all of the stuff that is overlapped by both. And that happens to be this area right here, which is the same thing as A minus B. So those are the complement laws. De Morgan's laws, I'm not going to show you a picture for this, but if we take A union B and we take the complement of the entire thing, or if we take A intersection B and we take the complement of the entire thing, what we do is we take the complement, we distribute it to the sets inside, and we flip the sign itself. So A union B, the complement of that, is the same thing as A complement intersection B complement. If we have A intersection B and we take the complement of that, we distribute the complement inside and we flip the sign. So that's going to be A complement union B complement. And that's called De Morgan's law. And in terms of text, okay, so a language example. If I say it is not 2 and it's not 3, what's another way of saying that? I can say then that it's neither 2 nor 3. Okay? So if we think of not 2 and not 3 being, for instance, I don't know, let's call not 2 just, let's pick an arbitrary capital letter for this. So this is like saying X complement intersection Y complement. Well, neither 2 nor 3, this is like saying, well, it's either X or Y, but actually it's not either of these, right? So if we think in terms of language, you know, X complement intersection Y complement is sort of the same thing as saying X or Y complement for the entire thing. So not 2 and not 3 is a paraphrase of neither 2 nor 3. So that's a verbal example of how this works. And you can pick adjectives too if that helps you. So maybe that's a way of putting it. So for instance, not a dog and not a cat. So I want to talk about all the things that are not dogs and not cats. So we could call this like D bar for not a dog, intersection C bar for not a cat, Another way of paraphrasing this was I am looking at something that is neither a dog nor a cat. So out of all the things that are dogs or cats, I'm not looking at either of these. So these two expressions are equivalent, and I think language is probably one of the better ways to look at this. So I want to take a look at how these are used in a proof. So we're not doing this example today, I just want to show you step by step of how these laws work. So next week we're going to learn how to simplify things as much as possible, but here. So for instance, in the first line, I have this B intersection C, and I have a complement surrounding it. I can use De Morgan's law to simplify this down to B complement union C complement. That's an application of De Morgan's law. In 4, I have a case where I have B union B complement. Now, this is everything in B or everything in B complement. Well, this is just the same thing as looking at the universe. So I can use the complement law to take B union B complement and simplify it down to the universe. In 6, I have C complement union the universe. So this is saying I want everything in C complement or everything in the universe. Well, this is the things that are in either C bar or the universe. Well, everything's in the universe, so I can simplify this down to the universe as well using the domination law. So this week, I just want you to become familiar with the laws. You don't have to start a proof from scratch and do everything, but I will give you some of these simplification proofs, and you'll just have to fill in the steps. So what law was used in the previous step, and typically what I do is I underline it. So I would underline, for instance, B intersection C all complement, and I'd ask you, okay, if it goes to this next step, what law was used for the conversion? And you'd say, oh, that's De Morgan's law. So when you do the problems, have the chart beside you. There's some practice questions on the Canvas page, and there's some practice questions in the mastery exercise too. If you have any questions, as always, feel free to post in the discussion board, and I will get to you as soon as I can.